Welcome everyone to this lecture on the fundamentals of capacitive wireless power transfer as part of the IEEE Wireless Power Week and the IEEE Wireless Power Transfer School. I'm Khurram Afridi. I'm an associate professor at Cornell, and I do research in high frequency power electronics with one of its applications being capacitive wireless power transfer. It is a great privilege to be able to talk to you through this platform. I'm going to hide my screen so that you can concentrate on the slides instead, and then we get going. All right, so our presentation today is going to cover a few topics. I'm going to start off by talking about the history and applications of capacitive wireless power transfer. And then I'll talk about some of the basic principles about how the capacitive wireless power transfer systems work and define its basic architecture. Then I will compare capacitive wireless power transfer with inductive wireless power transfer. You've probably seen a couple of lectures on that already. If you haven't, I'd recommend that you go see those. I will then do a case study on capacitive wireless charging used to charge electric vehicles. And then I'll give you some pointers as to where you can go to learn more about this topic if you're interested. All right, so let's begin with the history and applications of capacitive wireless power transfer. It's over 120 years ago that Nikola Tesla actually first demonstrated the concept of capacitive wireless power transfer. And yet we're still talking about it as if it is something completely new. And it is almost completely new because of how difficult it has been to achieve high power levels when you have large air gaps. And that's actually what we're going to be focusing on today in today's lecture. But back to Nikola Tesla, back in 1891, he was demonstrating how you could light up tube lights by putting them between two metal plates separated by quite a distance. You can see that on the left-hand side photograph. And by having high frequency voltages being applied across those plates and getting the electric fields between those plates to high enough levels, he was able to demonstrate those tube lights lighting up, as sort of shown in the caricature on the bottom right. Now, Tesla started it all. In fact, Tesla took it one step further. We're talking today about dynamic wireless charging, and Tesla had thought of that as well. Here on the left, you can see one of Tesla's, a photograph from one of Tesla's patents from 1894, where he's proposing to basically deliver power on the go to a tram that's basically riding on a street. And again, the energy is being transferred to this moving vehicle through high frequency electric fields. And sort of the return path in this case is coming back through the wheels, which are making contact with the ground. Right. Now, over 110 years pass before this idea is revived. And as I mentioned, it wasn't easy. I mean, Tesla postulated and was able to demonstrate at low power levels how this could be done. But to realize this in practice has not been easy. And so the field was kind of put on the back burner. In fact, inductive wireless power transfer, which uses magnetic fields, took off much faster, although it took its time as well. But back in the 1970s, people started working on delivering magnetic field-based energy to moving vehicles, although they didn't succeed at the time. But capacitive wireless power transfer took many more decades before it was revisited. And it was revisited in 2005 for applications very different, to at very small powers, at very small gaps, and really to charge or provide power to small chips or silicon ICs, where you were wanting to stack them on top of one another in the sort of three-dimensional packagings. And so the power levels here are milliwatt level of powers. Distances are negligible, sub-millimeter level. In fact, essentially the separation doesn't even have air in between that. Um, and that's how it got started, um, through this first paper on the left that you're seeing. Other people started to explore other applications of capacitive coupling. The one on the right shows a work done by Viponen from Finland, using capacitive coupling to provide power and signal to transducers that are an instrumentation that's connected to uh, for biomedical applications connected to human beings. And so for safety concerns and for noise immunity reasons, they wanted to use some kind of isolation, and they investigated capacitive isolation in this case. Again, the power levels were very small. They were delivering of the order of sub-watt levels of power, and they were also using, in this case, it wasn't even wireless because they were using lumped capacitors to create that isolation. So the distances involved were again very small. Uh, People started to explore other applications, what we would imagine more like the capacitive power transfer applications of today. In 2008, Patrick Hu and his colleagues investigated the use of capacitive coupling for small robots. In this case, a soccer playing robot, which would basically run out of energy, go to the side of the field, and essentially come very close to a couple of plates and get charged that way. Again, the distance here was very small because essentially there was just some dielectric material between the plates, and so negligible distance. Um, the dielectric itself was like a millimeter and was PZT, so high dielectric constant, so as to get as much capacitance as you could possibly get. And the power levels were of the order of low tens of watts in this case. Others, um, including Sudagar and Amiri from Iran, uh, proposed using capacitive coupling to deliver energy to biomedical implants, or things that were not too far deeply implanted in the body. Um, and they did very basic level of investigation, um, using basically just simulated kind of environment in which they were again delivering very low levels of power in PC board kind of emulators for human tissue. As you can see, the work was expanding and it was going global already. So with Tesla starting his work in New York, um, some of the previous work I've described was presented at conferences in Japan, and some of the work was done in Finland. Here now you're seeing work being done in New Zealand as well as in Iran, and it continued to sort of grow globally. Um, People were interested in certainly this area, but the general realization was that it's really hard to do capacitive wireless power transfer for higher powers and for larger distances. And so some of the work done back here in the US at Berkeley by Seth Sanders and his students and colleagues essentially investigated doing capacitive charging for things like cell phones, where again the cell phone was placed on top of the capacitive coupling plates. And so the distance was again negligible, and the power levels they were delivering were also again low tens of watts. In fact, in this particular work, it was even less than 5 watts. Um, and so again, low power levels, small distances. Over in Japan, Ohira and his colleagues and students proposed and investigated trying to get energy into a vehicle, but because they realized going through the air and the large air gap was going to be problematic and difficult, so they proposed going through the tires and putting a steel belt on the inside of the tire and having sort of metallic plates on the road and trying to bring the two pieces of metal as close as possible so as to create a large enough capacitance to get sufficient energy across. So up through this point, people are investigating, they're curious, but um, the general belief and the general trend is for low power, small gaps, as was also sort of the work in some of this early work from Dan Ledois at Wisconsin Madison, who, while as a student, investigated sort of getting small amounts of power for field windings in motors, essentially again through very small distance capacitive coupling. And then Murata, which is a company, actually tried to productize a capacitive based coupling system for first iPads and then laptop charging. Again, the distances here were very small, of the order of a millimeter, and most of it really being dielectric distances. And then they were also uh, basically at very low power levels. In this particular case, they got up to about 20 watts of power. So as you can see, the focus and sort of the general understanding was that for capacitive power transfer, you really need to have very small distances to make that feasible, and you can only get to low tens of watts of power level. So it wasn't until 2015 that people started to investigate large gap applications of, or large air gap applications of capacitive wireless power transfer. Some of the work was done by my group in partnership with Zoya Popovic, when my group was based out of University of Colorado Boulder. And we looked at the possibility of delivering high power to large air gap applications such as electric vehicle, going not through the tires, but rather going through the air gap, through the roadway clearance, which is at a minimum of the order of 12 centimeters. And one of the challenges there, as we will understand as I start to talk about the basic principles, is that you have to get to high enough frequencies to make the capacitive impedance look relatively smaller. And in this case, we investigated 6.78 megahertz power transfer. And in order to keep the electric fields, which necessarily get developed, and then sort of the fringing fields down, which will emerge from the sides of the vehicle, we proposed looking at multiple modules so as to cancel some of those electric fields by having them phased relative to one another. And that was one of the earliest papers looking at sort of automotive applications, or at least where the power was going through the air gap itself and not going through the tires. Just to mention the problem with the approach of going through the tires is that it's a highly dissipative way of delivering power, because tires have carbon black in them, which causes dissipation. And so it's not really a way in which to get high efficiency into the vehicle. Also, the contact area of the tires with the road is relatively small, so you don't really have a lot of surface area to get high amount of power into the vehicle that way. Soon thereafter, and done independently, was work done by Chris Mee, where they actually demonstrated 2.4 kilowatts of power across an air gap of about 15 centimeters, which is similar to the roadway clearance of an electric vehicle. However, they had to use rather large plate areas in order to get high enough capacitance, and they were operating at 1 megahertz. And that meant that really for them to scale to the power levels that would be needed for charging an electric vehicle, especially if the vehicle is moving, and so you have to deliver all the power that the vehicle needs for traction, that would become very difficult, almost impossible at the power transfer densities that they had, because they were using large plate areas, and it wouldn't be possible to fit larger than that or much larger plates underneath the vehicle to get sort of to the levels of tens of kilowatts of power, which is what our aim was, and the sort of the desire has been. So that's kind of sort of the history and background of some of the work related to capacitive wireless power transfer. There's a lot more work that's been done, so I picked some of it to kind of give you a general perspective. I tried to pick here sort of the work that was pioneering in its own particular areas. But let me now jump and talk about a little bit about sort of the basic principles of how capacitive wireless power transfer systems work. All right, so what is a capacitive wireless power transfer system? At its heart, you have essentially a capacitive coupler, which has two proportions. There's a forward path through which the displacement current goes from, in this case, the source towards the load, and then you have to have a return path. Each coupler comprises two metal plates separated by a distance. That's the air gap. That totally depends on your application. In the case of an automobile application, which is an area of my focus, that distance is at least 12 centimeters, which is the clearance of the vehicle from the road itself. So we can, to then understand this, we need to kind of model this coupler. And of course, this coupler can easily be modeled as, or these two couplers can be each modeled as a capacitor. So you've got two couplers. I call their capacitance 2C, since these two capacitors come in series with one another, giving you an overall effective capacitance in series with the load resistor R, whose value would be C. Now, given the geometry here, you can easily compute what that capacitance will be, or approximately you can compute it by a simple formula that you've probably learned in high school, which is epsilon naught A over D, A being the area of the plate and D being the distance between them. Epsilon naught is the permittivity of free space, which is a universal constant given here in terms of its value in farads per meter. And the challenge in capacitive wireless power transfer is the fact that epsilon naught is a really small number. And so for reasonable values of A and D, those that you would typically encounter in, for example, an electric vehicle application, this capacitance comes out to be really small. Just to put some, give you some perspective on that, we'll look at numbers in a minute. But first, let's talk in terms of, if we want to deliver power now to this load, what do we have to do? Well, you can use phasor analysis to get a formula for how much power you would deliver to the load, which here is modeled as a resistor. And you're essentially in one of two regimes. Either you're operating at a frequency that's really high, so that your capacitive coupler essentially looks like a short circuit, right? And in which case, there's no voltage drop across the capacitive coupling, and all of your source voltage appears across the load, and you're able to very nicely deliver power to your load. However, for most applications, that frequency that you need to operate at to get that capacitance have very little or negligible impedance is super high. And so for most applications, you're typically operating well below that frequency, which would, in terms of radial frequency, be given by 1 over RC. And so you're operating well below that. And in that regime, essentially, your entire applied voltage is falling across these two series capacitors. And you can essentially think of the power being delivered as by first computing the current that's going through those capacitors, which is basically the voltage applied divided by the impedance of that capacitance, which in magnitude is basically 1 over omega c. And then I squared R gives you the power that's delivered, and the factor of 2 comes because you've got a sinusoidal source in this case. All right, so we certainly see that getting power across is going to be challenging as long as you're operating at low frequencies or lower than this 1 over RC knee frequency, where sort of things start to kick up. And just to get a sense of the numbers, let's look at an EV charging application where the roadway clearance is the distance between the plates. It's 0.12 meters or 12 centimeters. Assuming the plate diameter is 22 centimeters or radius of 0.11 meters, you get an area which you can compute as from pi r squared. The capacitance, therefore, or 2 times C, comes out to be 2.8 picofarads. And so C, which would be the effective capacitance, is going to be half of that when you put these two capacitors in series. So it's only 1.4 picofarad of capacitance, really, through which you have to transfer this energy. So assuming you want to transfer 4 kilowatts of power, and if you assume the battery voltage is 400 volts or thereabouts, that gives you an effective resistance value of about 40 ohms. Assuming that you're operating at a radial frequency, which is associated with operating at a frequency in hertz of 6.78 megahertz, you can plug into the formula that I provided earlier to figure out how much voltage would you really need on the source side in order to deliver 4 kilowatts of power to this load. And it turns out that you would have to be at over 230 kilovolts in order to get that kind of power across. So clearly not happening, right? So this obviously is not the way to do it. And the reason we used this approximation for calculating the power is the fact that that knee frequency that I just talked about is more like over 1 gigahertz. And so clearly when you're operating at 6.78 megahertz, there's no way you're going to be able to get up to where the capacitor starts looking like a short circuit, right? Now, why can't I operate things at a gigahertz? Well, first of all, you have to generate this sinusoidal or whatever square AC voltage. Is only the AC current will go through the capacitor. And to do that, you would need switches that can switch that fast. And if you look at the kind of switching losses that you would have, um, a quick calculation will show you, if you looked at even the best quality devices out there, that you'd be losing kilowatt scale of power in those switches. And so it would just not be feasible for you to operate in the high gigahertz regime with such high voltages, because just the output capacitance related losses in those transistors would basically destroy those transistors. And so really you have to go look for another solution. And that solution is essentially what Tesla also realized, which is you use resonance. And in resonance, what we're doing is we're taking the reactive impedance that is given by the capacitive coupling, which happens to be a negative reactance, and you cancel that out by adding inductors in series, and those inductors provide positive reactance, and hence the overall net impedance of this path drops down. Now, if you were to exactly operate at the resonant frequency, which would be given by 1 over square root LC. Again, I've split these inductors symmetrically because just to kind of keep the circuit overall symmetric, you could shift both the half-sized inductors to one side and just make it one inductor. But just for symmetry, I'll keep it like this through this presentation. And we'll talk about sort of how you would sort of design these in a little while as well. But if you operate at omega equal to 1 over square root LC, which is the resonant frequency, then essentially the impedance of the capacitors or the coupling capacitance and these inductors you've added for canceling that reactance, the overall impedance would be 0, and you would deliver essentially power equal to V squared over 2R, and again the factor 2 coming from the fact that you've got a sinusoidal voltage source. All right, so that's all great. However, there are some issues associated with this design. This design would be a workable design, but it isn't what I would call an optimized design. And this is what would be called series compensated design. The issue here is that the value of the inductor that you need to compensate is given by 1 over omega squared C. So if C is really small, and if the omega that you want to use, which is your operating frequency, is reasonable, so that it's not super high, then the inductor size or the inductance you need is quite large. And so that um, may become a, an issue in terms of the size of the system. Um, Also, the losses in the system, there's going to be, here we've kind of assumed that the inductors are ideal. In reality, the inductors will have some quality factor, which you can think of having some sort of series resistance because of uh, the AC losses in the wire itself, as well as, of course, the DC losses. And so this design can be further improved. So one way to kind of think about what we want to uh, do in making sort of this design better um, is somehow make this inductor look a lot bigger than the inductance value that we're using. The other thing we'd like to be able to do is reduce the amount of current, this displacement current I, that's passing through the capacitive coupler. The reason for that is because the voltage that develops across the capacitive coupler is given by the impedance of this coupler, which is basically equal to 1 over J 2 omega C times this current, and that'll give you the voltage we see across this coupler. And the larger that voltage, the larger the fringing electric fields will be. And those fields have to stay within a safety limit in order for the system to be safe for people who may be sort of walking around close to it. And so we'd like to keep this VC voltage small, which means we'd also like to keep this current I small so that um, we don't develop that large voltage VC. So one goal is to reduce the current I going through the coupler. The second goal is to make the inductor L seem bigger than it is. So we can achieve both of these goals by essentially adding transformers on both sides of the coupler. Now, in reality, I'll show you that we don't really add transformers, but this is a good way to understand what we're trying to achieve. So, but for now, think of them as essentially transformers. And in fact, you could use transformers if you were operating at frequencies low enough where you can get core material that has high enough permeability. Turns out that once you get well above a few megahertz, you're not going to be able to find good core materials to form such good transformers. So typical applications, we will not be using transformers, and I'll show you what we do in that case, but the concept is clearer this way. So let's go with it. Right, so if we add these transformers, you can clearly see, because going from left to right, we're basically boosting up the voltage by a factor of n being greater than 1, then the current is being reduced by a factor of n as well. And the same thing is happening on the load side. So we're delivering some load current, which is um, has to be of a certain value in order to deliver a certain amount of power, I squared times R over 2 to the load. Then if you go left from there, you can see again that you're boosting up the voltage, so you're reducing the current. So clearly we've reduced the current I that goes through the capacitive coupler, hence reduced the voltage VC. So we've met that objective. The second thing, if you remember from an early circuits class that you may have taken as a sophomore or so, that when you pass an impedance through a transformer, the impedance gets multiplied by the square of the turns ratio. So the inductances reflected towards the side of the coupler will essentially increase in value by n squared. And so effectively now you have a much larger inductance compensating for the 2C coupler impedance, even though, or coupling reactance, even though you don't really have that large inductance. And so now you can see that you can pick an inductance value L by also taking into account this factor n, which is greater than 1, and hence allows you to use a smaller inductance. All right, now, as I mentioned, in reality, at high enough frequency, especially in sort of the 6.78 megahertz and above range, you're not going to be using transformers. And instead, what you will do is use what's called a resonant matching network, whereby you achieve the same kind of voltage step up from the left-hand side matching network, which is formed by an inductor with a shunt capacitor. And, and then the reverse happens on the other side, where you've got a capacitor followed by an inductor to essentially bring the voltage back down, or you're essentially stepping the current back up. And to see how this increases your voltage, think in terms of this being like a parallel resonant converter, where you essentially have an LNC which resonate now in parallel instead of in series. And if you were to essentially plot the voltage Vp, which appears across the capacitor voltage at the appropriate frequency, where L2 and Cp start to resonate with one another, you will get a large boost in voltage. So this essentially is the fundamental starting, or we should say starting building block of a modern capacitive wireless power transfer system, whereby we have some source, we have a matching network, then the coupler, and then a reverse matching network down to our load. Now, in reality, we don't really start off by a high frequency AC source, and we typically don't have an AC load, although we could if it was, say, just a heating um, application. In reality, we start with some DC source and have a DC load like a car battery. So in which case, we essentially have to use an inverter to go from our DC supply and go to a high frequency AC output at the inverter. And then the rest of the system stays the same until we get to the load side, where we essentially rectify this high frequency AC signal and charge the battery from the rectified current. And the capacitors at the sort of before the inverter and the capacitor after the rectifier are just for filtering this high frequency pulsation so as to give you DC currents going into the battery and DC current coming out of your voltage source. All right, with that kind of completes our sort of introduction to the basic principles of capacitive wireless power transfer. What I'm going to talk about next is how we take this basic architecture. And again, this is kind of taking that same thing that I just showed you, but giving that in a more block format, because you can actually use multiple different types of matching networks. And the basic purpose is on the primary side, they're providing voltage gain and compensation, which is reactive compensation. And then on the secondary side, they are providing a current gain and also providing the remaining part of the compensation needed for the reactive coupler. So with this block diagram, the next what we're going to move into is do a quick comparison between capacitive and inductive wireless power transfer. After all, inductive exists. So why are we even bothering about capacitive? So to look into that, let's jump right into that. Okay. So in terms of the basic principle, we talked about how capacitive works. So we've got a pair of coupling plates with electric field essentially acting the intermediary energy transfer mechanism. On the other hand, in a inductive system, we have two loops of wires. So think of them just the same way as you would think of a transformer. You run current through the primary loop, and that current produces magnetic fields. Those magnetic fields coupled to the secondary loop, where you induce a voltage, and that voltage essentially is going to feed your load. So the coupling mechanism is, instead of being electric field based, it's a magnetic field based coupling mechanism. In terms of the overall architecture, you'll see that they're almost duals of one another, very similar. So both require an inverter. Typically, these operate at high frequencies. What is exactly high and what is that frequency depends on the application. And also depends on whether you're doing capacitive versus inductive, as we'll see. In the case of the inductive system, rather than having a voltage gain on the primary side, you typically have a current gain because the magnetic fields are produced by current. So the larger the current on the primary, the bigger the field you'll get. So you're trying to get to a higher current in the primary coil. And then on the secondary side, you are then you have a voltage gain network in order to boost the voltage up, and you can step the current down before you rectify it and feed your load, right? Which, let's say, is a battery. Again, you could charge that, right? So very similar in terms of their architectural concept, but it's the bigger difference is the way you're coupling. One thing you'll notice is, and this goes to the heart of sort of the reason why capacitive wireless power transfer is attractive, is that the electric fields start and end on plates. On the other hand, in the magnetic field based system, the fields have to close on themselves. So they start, let's say, at the primary coil, and they loop through the secondary coil, but then they must return back through some return path and come back to where they started, right? So magnetic fields, because we don't have any magnetic monopoles, essentially have to end where they started. So you have this sort of a looping behavior, and this is going to impact uh, the sort of the design in terms of managing these fields, because these are high frequency fields. You don't want them to interact with people. And so for this purpose, we have to do a bunch of stuff. So let's compare inductive and capacitive at sort of at a high level. So as I mentioned, you in the case of the inductive system, you have magnetic fields that loop around. And since they loop around, but you don't want them to, for example, enter the passenger compartment of an electric vehicle, you need to provide some material that will guide those fields away from that part. And typically what you will do is you'll put ferrites behind the coupler. Ferrites have high permeability, which guide the magnetic fields or give a preferred path for the magnetic fields to go through, and sort of shift them away from going into the passenger compartment. So flux guiding and guidance and shielding is needed in inductive WPT, but not needed in capacitive because the fields terminate naturally on the other plate. We use ferrites in the coupler of an inductive system, but we don't need ferrites or other dielectric in inductive system for field guidance and shielding. And typically, for inductive systems, especially the ones operating at high enough frequencies, um, even in hundreds of kilohertz and above systems, you typically use Litz wire because of skin effect. If you're working with large currents, that is in high power systems, the wire would otherwise be thick enough that you would only essentially carry the current in the surface of the conductor. And so to make sure that the current goes through the entire wire, you use what's called Litz wire, which is a stranded wire, which is woven in such a way that um, all the wires in the individual wire strands see the same fields around them and therefore carry equal current. That is a fairly expensive wire, and that is needed for WPT. But in capacitive systems, the coupler doesn't have any wires, it's just made out of metallic plates. So that allows the capacitive systems to be a lot cheaper. Also, because the ferrites are heavy, the inductive systems tend to be substantially heavier than the capacitive systems. Those ferrites also add thickness. So unlike the capacitive coupler, you have a fair amount of thickness to this, which would be sort of the dimension coming out of the page here. Can't really tell the dimension here, but the capacitive coupler is a thin piece of metal, so it's very slender. All of those Litz wires and ferrites add to the cost of the inductive system. Also, the ferrites are ceramic materials and so fragile. The capacitive system is not fragile and so has all these advantages. Also, because the fields track the negative charges which are induced on the opposite plate, you tend to have better misalignment tolerance in capacitive systems, substantially better misalignment tolerance in capacitive systems as compared to inductive systems. Also, uh, time varying magnetic fields produce eddy currents. And so if you have metal objects lying around, say a Coke can near where you're charging, you would induce eddy currents in it, and that could heat it up and could potentially be a fire hazard if there were sort of hay or dry paper lying nearby. Uh, so all of these are benefits of capacitive wireless power transfer, which makes capacitive interesting and valuable to look at. The problem however, is that it's difficult to deliver high power across large air gaps in capacitive, as I mentioned in the beginning. And the reason for that is, if you look at the governing expression, which is a very simplified way of saying, well, what are the parameters that, for example, in the case of the inductive system, what is the sort of the voltage that you would induce on the secondary side? Well, it's proportional to what's called the permeability of free space. On the other hand, in the capacitive system, the current that, or the displacement current that is going to flow towards the load is proportional to the permittivity of free space. And there's a more than 5 orders of magnitude difference between the permeability and the permittivity of free space. And these free space values are also the values that are applicable to air. And so inductive systems have an inherent advantage, uh, and they also have an advantage because of the number of turns that you can add to your coils. And so there is a built-in advantage for inductive systems. The only way, uh, or at least the sort of the major way in which a capacitive system can catch up, is the fact that these induced voltages and sort of the displacement currents really depend on the rate at which either the source current is changing in the inductive system, or the uh, source voltage is varying in the capacitive system. And so by going at high enough frequencies, you can make the capacitive system catch up to the inductive systems. But that does mean that you have to operate at much higher frequencies compared to the inductive system in order to have commensurate level of power, which is essentially what makes capacitive wireless power transfer so much more harder, because developing power electronics to operate at such high frequencies, which means that for the kind of systems that I'll be talking about next, which is automotive or electric vehicle wireless charging, you have to go to um, high megahertz frequencies, whereby high means at least get to 6.78 megahertz, but even higher, the better. All right. So with that, let's look at a very quick look at the case study of electric vehicle wireless charging by capacitive means. Um, and I will go through this rather quickly and point you to references that you can read to learn more about it. And let's start talking about this application. So first of all, wireless charging of electric vehicles can be either stationary or it can be in motion, also known as dynamic. And we'll talk about both of those, but we'll start by talking about stationary first, because that's also going to help us then get to the dynamic part. So why are we talking about capacitive? I've already talked about sort of the advantages. They're sort of summarized here. I should point out that one additional advantage in this specific application is that since capacitive systems don't have ferrites, and ferrites are brittle, they're also, these systems would be easier to embed in the roadway. And if you had high weight traffic going over them, you won't crack those ferrites, right? But anyway, I've summarized those advantages that we talked about earlier in these slides. You can come back and look at these and read them on your own. For interest of time, I'm going to move quickly through these slides. All right, so as we mentioned, the big challenge in a capacitive system is you've got you've got epsilon naught, which is a very small number, meaning that your capacitive coupling is small. Since you have a very large air gap in this application, so you have to go to very high frequency operation. Also, in order to keep this current going through the displacement, or this displacement current going through the capacitive coupler small, you need to get a high voltage gain, which you're going to get through this matching network, and then you're going to have a reverse matching network to bring that down, and you have to compensate for this reactive um, impedance. Now, you have to do all of this while meeting safety standards in terms of field levels. The field levels that uh, and the safety limits that we follow are set by ICNIRP. Here you can see the chart at the bottom right, which shows sort of the field levels in terms of volts per meter that you have to meet. Now, the frequencies we'll be targeting will be in the megahertz, so the field levels are actually at their lowest required levels, or the safety levels are the most stringent in this regime. Um, and so really means we have a lot of work cut out in order to meet all of these requirements. Uh, let's talk quickly about the matching network design, because that's sort of what's going to help us get the compensation that we will need, as well as the voltage boost that we need. And I showed you just a simple L section. It's called an L section because it looks like an upside down L. You have an L section matching network that we looked at before. There's no reason why you couldn't cascade a whole bunch of L section matching networks to form a sort of a higher order multi-stage matching network on both sides. And then the question is, well, how many stages should I use, and how should I distribute the amount of gain and compensation that each stage requires? Now, this is fairly mathematically involved work, so I'll just give you sort of the highlights. You can set up this problem to optimize, for example, for efficiency of the overall system. You can get efficiency expressions for each of the stage of the matching network. The product of those efficiencies give you your overall efficiency. And you can express those efficiencies in terms of these Q factors. These Qs you can think of sort of like providing a gain. It's sort of the same kind of Q that you would have in any resonant network. And it's relative to the quality factor of your inductor. The QL here essentially measures the losses in your inductor. And so what you're trying to maximize is um, this term, which in effect means you're trying to minimize the sum of all of these Q effectives. If you go through the math of setting this up um, as a constraint optimization problem, because you've got a number of constraints to meet, and I will not talk about all those constraints in this quick talk, but you can read the paper, which I will talk about I'll point you at the end. You come up with results which look like this. And so first question to answer is, well, how much of the gain and compensation should I get from my first matching network, or the primary side matching network, versus the secondary side matching network? The key result here is that, well, how much gain you get from the first matching network versus the second matching network really depends on what your input DC voltage is relative to your battery voltage, right? Because if you you need to boost the voltage from primary to secondary, well, you'll need to step down this current. If on the other hand, the battery voltage is lower than the input voltage, you'll have to um, increase this output current. So let's say if for example, the two currents were the same, that means the battery and input voltage were the same. Well, in that case, I out over IN would be 1, in which case you essentially provide the same amount of gain and the same amount of compensation from both sides. On the other hand, if, for example, you had to step uh, down the voltage, so the VBAT was lower than your input voltage, and you needed a higher output current, well, in that case, you would basically provide more current gain from the second uh, network, which is the vehicle network, which is essentially means that you would um, boost up this current more here, then you step the current down going backwards on the primary side. Now, the amount of work or a matching network has to do in providing current gain or voltage gain um, uh, basically imposes in a sense, a stress on the matching network. And so if order to get an overall maximum efficiency, it turns out that what you'd like to then do is, for the matching network that is providing more current or voltage gain, you have it provide the less compensation. So for example, if you had I out over I in as 2, so the vehicle side network was providing a bigger current gain, then the vehicle side network would provide less of the compensation and let the roadside network provide more of the compensation. Um, we can also look at how we should distribute the compensation and gain within one side of the network. And here again, you can see that the um, the uh, the way this comes out is that the compensation, you want to put most of it closest to the actual coupler itself. And that kind of makes sense, because closest to the coupler, you have the smallest amount of current. And when you have the smallest amount of current, you can afford to have a larger inductance without having a lot of losses, because a larger inductance also means larger resistance for a given quality factor of inductor. And so by using a larger inductance close to the coupler allows you to keep your losses in control while providing more compensation. And again, the same is true on the other side. As far as the voltage or current gain is concerned, you try and provide as much of that early so that you get up to high voltages quickly, and then whatever difference is left, you provide that from the last stage. So essentially, you try and max out the gain from the early stages or the stages further away from the coupler. There's actually interesting results related to how many stages you should use. Turns out actually that the more the stages you have, the higher the overall efficiency you're going to get. But that efficiency starts to reach a maximum value. And if you're going to limit the number of stages on one side, then it turns out that on the other side, there's also an optimum value for that number of stages on the other side that is going to maximize efficiency. Talked about the maximum efficiency. So if you did have infinitely large number of stages, it's still only going to get up to a maximum efficiency that's limited by the quality factor of your components. In this case, it's limited by inductor quality factor, because the inductor quality factor is typically substantially smaller than a capacitor's quality factor, the capacitors being more efficient or less lossy. And you can get analytical expressions for these, which are sort of shown here. And this tells you what's the maximum efficiency your system can deliver, or at least the matching network can deliver, given sort of your design parameters, where P out is the output power, A is the area of your coupling plates, D is the air gap between the plates, F is your operating frequency, input voltage and output voltage are V in and V bat, and K depends on sort of the kind of rectifier and inverter topology you're using. All right, so let's try and wrap this up quickly. And so just to give you a sense of how this benefits us in our design, if we use the approach that we just mentioned, where you're sort of distributing the compensation and gain across these networks, what you will see is that it ends up giving you a much better trade-off in terms of power transfer density and efficiency, as compared to an approach which I refer to here as the conventional approach. Conventional approach, because in earlier work by convention, it was believed that by putting all of the compensation right close to the coupler is the best approach. And as I pointed out, that does sound like a reasonable approach, because you do have the lowest amount of currents there, but it turns out it's not the best approach. You shouldn't put all your compensation right next to the coupler, but you should actually distribute the compensation. All right, very quickly then, what's the benefit? Well, the big benefit comes when you're trying to reduce the air gap voltage. Remember, I mentioned that you want to reduce this air gap voltage because that will then allow you to have smaller fringing fields. And so as you go to lower air gap voltages, this proposed approach that we just discussed gives you a higher efficiency compared to the conventional approach. All right, the last major topic that I'm going to talk about, and then we'll go quickly through some results, is the coupler itself. Well, we've been kind of thinking of the coupler as just two plates forming two capacitors, um, linking those plates, and so the power has to go through these capacitors. But in reality, the vehicle environment, which we're looking at, has a lot more capacitors, right? There are capacitances pretty much from every metallic object to another metallic object. And so there are these parasitic capacitances which will suck away the energy. If you're trying to deliver energy from, say, this plate to this plate, that energy is not necessarily just going to go there, but rather can be shunted around in different pathways. In fact, some of these parasitic capacitances can be larger than their main capacitance. And so we've got to deal with that somehow. If we convert that into a circuit model, it looks like this. And you see that there are a whole bunch of these extra capacitances in addition to the C plate, which is the one that we really care about. And if in particular we look at some of these capacitances and see their effect, you can see numerically that if you have this capacitance, which is between the roadway and the ground terminal of the inverter, that'll suck away a lot of your power. Same thing will be true for the capacitance on the other side, on the vehicle and the rectifier ground. And you can see how sort of having non-zero values for those capacitances decreases the power that you can deliver. So in order to solve that, one approach that we've utilized is to basically use the symmetry of the structure to null out the power leakage. And you can do that by taking the L section matching network inductance and splitting that inductance into two halves, one at the top, one at the bottom, so as to produce symmetric voltages in this network. And in fact, if you think about this, you've got this inverter producing positive negative voltages here, and by symmetry, this node here labeled R, which is represents the roadway, would have 0 volts across it because you've got positive voltage here, negative voltage here, and this sits in between those positive and negative, and so it's at 0. Same thing with the vehicle. It basically sits between them, is at 0. And so what that does is basically put 0 volts here. This is 0, so it effectively nulls out this capacitance because you've got 0 volts across it. Same thing with this capacitance. It nulls it out, and a 0 from here to here also nulls out this capacitance. And so you can see that if you basically go to a split structure, you go from power dropping initially to basically power not dropping at all. And so we can eliminate those capacitances through this means. The remaining capacitors are still a jumble, but we can start to now eliminate some of them by simplifying this network through the following logic. First, observe that these two capacitances are actually carrying the same current because you have a current coming down from here. And this node is at the same potential relative to this as this potential is relative to that, because this voltage is positive something and this is the negative of that voltage. And so this is right in the middle. So the same current goes down here as was coming through here. Hence no current from here leaks out. So you can basically disconnect this node from here and just move it out. Similarly, you can play the same trick on these two capacitors and move that out. Now you've got these series parallel combination of capacitors, which you can all combine together and merge them with these capacitances here. Okay. The next you can do is look at these diagonal capacitances. If you use two-port network theory, you can actually model these capacitances as if they were essentially shunt capacitances here, and they subtracted away some of the current that was going to go through here, so it effectively reduces the values of these plate capacitances. So you can take those and you can again model them as shunt and capacitances that reduce the value of the capacitances of your plate. Now you can actually take these capacitances and you can use them as part of your matching network, or you could actually realize your entire matching network from these parasitic capacitances, which is essentially what we do. All right, so with that, now I can share some results. So here are some systems that we've built at 6.700 megahertz. You can see progressively our various generation systems and how we were able to reach 1200 watts with power density of 51 or so kilowatts per meter square. That means in a meter square area, we could deliver 50 kilowatts or more of power at efficiencies that are reasonable, is approaching 90%. This is operating at 6.78 megahertz with an air gap of 12 centimeters. We wanted to do better, so we looked at where our losses were. Turns out that most of our losses are in our matching network inductors. So we worked on improving their performance. One, you can improve the performance by coupling these inductors, making them essentially look bigger than they are, because now your flux from this inductor is coupling into this inductor, and hence amplifying the inductance value. And you can operate these at a higher frequencies, which allows you to shrink again the inductance that you require. And so you go from 6.78 megahertz inductors, which are uncoupled, to a coupled 13.56 megahertz inductor, which looks already smaller. We can further optimize. In fact, you can see going from that 13.56 megahertz inductor, which had a Q quality factor of 1000, which by itself is very good, but we were able to further optimize using various innovative designs where we are using these interleaving of multiple layers, yet achieving sort of a compact design to get to quality factors as high as 2000 with some of our TIFF designs. Now, with sort of these higher performance inductors and operating at higher frequencies, we were able to get to power levels of approaching 37.5 kilowatts of power, and power densities again at that 50 kilowatt per meter square. And these are systems operating at 13.56 megahertz. And efficiencies which are now even better. Lastly, I'll close out with a few more topics just very quickly. One is about safety. So I mentioned earlier that you want to keep your field levels low. And we keep those field levels low to begin with by sort of making sure that the displacement current going through the capacitive coupler is small, so as to create a smaller voltage across the capacitive coupler, which keeps the fields low. But now you can add multiple modules, and by applying the appropriate phase to each of these modules, you can actually cancel out the external fields, and you can here see that effect where the field levels have been reduced by sort of using multiple modules. Also demonstrated that in practice by having multiple modules, where if you run those two modules, just if you run one of those modules, this is sort of the field levels you will get. If you run two modules, it'll obviously double the field if you run them both in phase. But if you run in anti-phase, you can cancel the external fields and actually have less field than from a single module. And so that's one way you can reduce it. Another area of interest is, and I talked about in the beginning, that there's stationary charging, which is what we've been talking about now. But what if things are moving? Well, if things are moving, the biggest challenge is the fact that your coupler reactance is changing, because your coupler reactance depends on the distance between the plates. And so as the vehicle sort of moves, that coupling reactance changes. Also, if you have a vehicle with a higher road clearance come by, then you have a different coupling capacitance. So to deal with those situations, you need a way to kind of be able to compensate for these coupling reactances. Now, remember, our systems run at a fixed frequency. And the reason we pick these frequencies of 6.78 megahertz and 13.56 megahertz is because they fall within the ISM band, the industrial, scientific, and medical bands, where you're sort of allowed to operate um, at at at, um, at power levels and at and your sort of constraints in terms of electromagnetic fields is sort of less constrained by the FCC. So we want to stay at these frequencies, and so we can't tune our systems by changing frequencies. So we instead need a different way to do that. And what we've developed are basically new approaches for doing that rely on, um, in this particular example, by a special kind of a rectifier, which can inject extra reactants into the system. And I won't go into the details of how this works in interest of time, but I'll point out a paper you can read if you're interested. But essentially the way it works is that you're splitting power through two rectifiers rather than having a single rectifier. And each rectifier has of these two, one has a positive reactance in front of it, the other has a negative reactance. And by splitting how much power goes through one branch versus the other, you can provide a continuously variable amount of reactance that the system sees. And hence you can basically, by controlling the power going through these two rectifier branches, control the impedance that you're seeing looking in. Now you can change the amount of power in this case with this design simply by changing the output voltage of these rectifiers, which you can do using these DC-DC converters. And so it's a fairly simple control. You just change voltages and you're able to shunt how much power goes through one branch versus the other and hold the total power constant. And that allows you to essentially change the reactive compensation you're providing. With the system, we've demonstrated that you can have uh, sort of a much larger misalignment tolerance, so that if a vehicle, say, is driving from here, you can start to deliver power even before it comes fully on top of the charging pad, and essentially start to deliver power along this blue line. And if you didn't have that system, you'd only be able to deliver power along the red line. So you can enhance the amount of energy delivered to the vehicle by 80% or so in this case. And you can also deal with sort of height variations in vehicles through the system. So with that, we come to the end of the material I wanted to talk about. Now, for those of you who are interested in learning more, here are the references that I've used in this talk, or sort of the topics that I covered, and some of the early work that I mentioned is out of sort of the references listed here. You can read these on your own time, as well as additional references provided on this screen, which include some of the work that my group has performed in this area as well, including some of the very recent work. Finally, if this area excites you and you'd like to work in it, you're welcome to write to me. My group at Cornell, which is the High Frequency Power Electronics Group, works in this area as well as in other applications of high frequency power electronics. And so I look forward to hearing from any and all of you who may be interested in learning more. And with that, let me thank you for watching this video. I wish you a great WPW 2021, and hope you enjoyed this lecture. All right, take care.